parent functions and how we can transform them. These parent functions should look familiar to you. And when we look at the standard form with which we can write an equation or a function, there are a couple things that happen. The plus or minus in the front tells us whether or not we're going to reflect across the x-axis. The A tells us whether or not we're going to vertically dilate, so we're going to stretch it out or compress it downward. The plus or minus on the inside of our function tells us that we're going to reflect across the y-axis or not. The D tells us whether or not we're going to translate left or right. And B tells us if we're going to translate move or shift up or down. The C in the middle determines whether or not we're going to horizontally stretch or compress. Let's first take a look at a few examples that are associated with our B, whether or not we're going to shift our graph up or down, and how we can determine that. We will shift our graph up if we have a positive B on the outside of our function. We will shift our graph down if we have a negative B. Now, if we are translating on the inside of our function, so it's on the inside of whatever our function is doing, if we have a negative D value, we're going to shift right. And if we have a positive D value, we will shift left. So let's look at a couple of examples that shift vertically and shift horizontally. Graph each of the following, and before doing so, describe how each graph can be obtained from one of the basic graphs shown earlier. We have our function g of x is equal to x squared minus 6. I see that x squared, so I know that my parent function is x squared. I also see that the subtract 6 piece is on the outside of whatever is happening to my function. So we could think of this as f of x minus 6. This tells me that we're going to shift our graph down 6 units. We can then compare some points on our graph of f and g. Our, again, parent function, where I had plugged information in, is from x squared. So when I take negative 3 squared, we get 9, 0 squared is 0, and 2 squared is 4. Doing the same with our g function, we would have negative 3 squared, which is 9, 9 minus 6 is 3. 0 squared minus 6 gives me negative 6. And when I take 2 squared minus 6, or 4 minus 6, we have negative 2. When I compare the y-coordinates of my functions, I see that they fall 6 units. So they are 6 less than the corresponding point from our function f of x. And then we can plot some of these points to graph. Negative 3, 3, 0, negative 6, and 2, negative 2. Let's try another graph. Here I have the function g of x is equal to this absolute value of x minus 4. So our parent function is the absolute value of x. And notice that my parent function, the subtract 4, is on the inside of our function. This tells me, since it's on the inside, that we're going to shift left or right. And it's the opposite of what we think. So you might think that we want to subtract 4, when in reality we want to just simply move to the right. So then let's compare the points from our parent function to our g of x function. Our parent function would provide us with negative 4, 4, 0, 0, and 6, 6. Whereas our current function, our absolute value of x minus 4, provides us with 0, 4, 4, 0, and 10, 6. When I look at my x coordinates, I see that they are 4 more than the parent function. So let's take a look at this graph using our Desmos calculator. I'm going to put in our parent function, which is f of x equal to the absolute value of x. And down below, I'm also going to put in our function g of x is equal to the absolute value of x minus 4. And you can see as we built it here that our points are nearly this, they are the same. Every point is just shifted to the right 4 units. Our next example here has both a vertical shift and a horizontal shift. Notice that we've got the square root of x plus 2, and that's inside the function, and then we subtract 3. So we're looking at our parent function of the square root of x. We know that the x plus 2 on the inside tells us that we need to move left because it's the opposite way of which we see since it's inside the function. So we're going to move left 2 units. And the negative 3 on the outside tells us that we need to shift our graph down 3 units. So together, when we put them both with the shifting left and the shifting down, we know that our parent function is going to be shifted left 2 units and down 3 units. Let's see what this might look like on Desmos. We're going to start by putting our parent function in the graph so that we can see where we're going from here. Our parent function was the square root of x. And now let's build our new function, which was the square root of x plus 2. Here we see that we are shifted to the left 2 units. And I'm going to make sure I use my arrow to move outside of the radical so it doesn't keep building inside the radical. So shifting outside the radical, subtract 3. So I can see now that each of my points have shifted to the left 2 units and down 3 units. So this particular point is 4, 2, is shifted to the left 2 units and down 3 units to give me this point here. Let's talk about reflections across the x-axis and the y-axis. If we have a negative on the outside of our function, that tells us that we're going to reflect across the x-axis. If our negative is on the inside of our function, we're going to reflect across the y-axis. We also know that if a point xy is on the graph of our function, then also x negative y is on the graph of y is equal to the negative function value. And similarly, if I have negative x, y is on the graph of y is equal to the function where the x is negative on the inside. So notice where my y is negative here. Oops. And I know f of x is fancy wording for y, belongs here, and that my negative x pairs here. Just another way to write it. Graph each of the following. Before doing so, describe how each graph can be obtained from f of x is equal to x cubed minus 4x squared. So this is acting like our parent function because we don't have a parent function with x cubed and x squared together. So this is going to be our parent function. We want to know how g of x, which is negative x cubed, minus 4 times negative x squared can be obtained from our parent function. Well, when I look at my parent function, if I were to replace negative x, like this example here, do all of my x's turn negative on the inside? When I replace my negative x, I'll have, with negative x in my f of x function, I have negative x cubed minus 4 times negative x squared. Well, hey, that gives me exactly my g function. So when I manipulate taking negative x to my parent function and substitute that in, I get my g function. This tells me that we are going to reflect across the y-axis. And let's graph on Desmos to verify. But before we do that, we say that if our values x, y is on the graph of f, then therefore negative xy is on the graph of g. As an example of this particular graph, 2, negative 8 is on our graph of x, and you can verify by plugging those numbers in. Then negative 2, negative 8 must be on the graph of our g function. Let's take a moment to graph both the parent function and the g function to verify that we are actually crossing and reflecting over the y-axis. It gave us our parent function of f of x is equal to x cubed minus 4x squared. So it looks something like this. I'm just going to zoom out a little bit. We've got some points on here. If we're reflecting over the y-axis, we would expect these points to be moved this direction. So negative 4, 0, and this point to move over here. So negative 2.667, negative 9.481. However, 0, 0 should stay where it's at. So let's graph our g of x function, the function that we believe and we know is reflected across the y-axis. Negative x cubed minus 4 times negative x squared. And just as we suspected, our point 0, 0 stays the same. We have 4, 0, and we reflected to negative 4, 0, and then we can see these other points as well are also a reflection across the y-axis. Using the same parent function, which was f of x is equal to x cubed minus 4x squared, let's see how it's manipulated to obtain 4x squared minus x. So notice at this point, if I were to rewrite these, what we did then to get here, we took our whole entire function and multiplied it by -1 and distributed. So I took my function and I took -1 to the outside, and then we distributed it through, providing us then with our h of x function. Since we multiplied everything on the outside of our function by a negative, this tells us that we're going to reflect over the x-axis. So if xy is on the graph of f, then x negative y is on the graph of h. So for example, if we had 2, negative 8, then reflecting across the x-axis would provide us with 2, positive 8. Let's take a moment to look at Desmos. Let's also look at our parent function again using our second example. Again, our parent function was f of x is equal to x cubed minus 4x squared. And the function that we're looking at right now is h of x is equal to 4x squared minus x cubed. This time, notice just as we had suspected, our graph is reflected across the x-axis. So everything is flipped and mirrored across the x-axis. At this point, we now can focus on vertical stretching and shrinking and horizontal stretching and shrinking and how that might affect our graph. So there's a lot of definitions here. However, if you take it slowly one by one, then we'll be okay. So the first part here talks about stretching vertically, and the second part here talks about horizontal stretching or shrinking. So when we want to stretch vertically or shrink vertically, we need to look at the value of A. So if the absolute value of A is greater than 1, then we are going to stretch vertically. If it's a fraction between 0 and 1, we're going to stretch. We also know that if our a value is negative, we will reflect across the x-axis. If we have our c value on the inside, so attached to the x value on the inside, this tells us if we're going to shrink horizontally or stretch horizontally. So if our value is greater than 1, we're going to shrink horizontally. Or if our value is a fraction, we're going to stretch it out horizontally. We also know that based on the positive or negative on the inside, that our graph, if it's less than 0, will reflect across the x or y axis, just as we had done in a few examples previously. Here we have a graph of a function. There's no formula for this function, but we're going to take this and manipulate this a little bit in the remaining examples to see how it all puts together. On the left here, I have our points from the previous page that go in order from left to right. -5, 0, -2, 2, 0, 0, 2, -4, and 4, 0. So keep that picture in our mind of what it looked like from the previous slide. Here we want to take our function f of x. Again, we don't have any particular formula for it. We just were given 5 points. And we want to take a number times f of x. Because this number is greater than 1, this tells us that we're going to stretch. Well, if we're going to stretch, that means that we're going to multiply our graph, or excuse me, if we're stretching vertically, that means our y values are going to change because we're moving up or down at a greater rate. That means I need to take my y and multiply it by 2. Because we know f of x is fancy wording for y. Oops. So looking at my original points of -5, 0, when I multiply my y value by 2, my -5, 0 will still stay -5, 0. -2, 2 will be increased to -2, 4. 0, 0 will remain the same. We will also have 2, -8, and 4, 0 will remain the same. Graphing these points then, I'll have -5, 0, -2, 4, 0, 0, 2, -8, and 4, 0. So kind of putting it all together, I see that our graph certainly did stretch vertically. Our next example, we have half of f of x. We're going to use our still parent function with our original points of -5, 0, -2, 2, 0, 0, 2, -4, and 4, 0. How will this half affect our graph? Notice the half is on the outside of our function, so then each y value will be multiplied by 1/2, resulting in a vertical shrinking. So our graph should get shrunk down vertically, so it'll get closer to the x-axis. When I multiply then my y values by half, we'll still have -5, 0. However, 2 times half gives me 1. 0, 0 will remain the same. -4 times half is -2, and 4, 0 will remain the same. So let's see what our graph might look like. -5, 0 stayed the same. -2, 1, 0, 0, 2, -2, and 4, 0. So here, notice we got much closer to our x-axis because we shrunk vertically. This time, let's multiply on the inside of our function. Here we have f of 2x. So since this number on the inside of our function is 2, and 2 is greater than 1, we know that we are going to horizontally shrink based on our definitions. If we're horizontally left or right shrinking, that means that our x value is going to be changed. So we need to change our x coordinate and divide each x coordinate by 2. Where our y coordinate this time will stay the same. So -5 divided by -2 provides us with -2.5. -2 divided by 2 is -1. 0, 0 will remain the same. 2 divided by 2 gives me 1, and 4 divided by 2 is 2. So if we are horizontally shrinking, that means we're going to compress ourselves closer to that y-axis. Let's see what that might look like. -2.5, 0, -1, 2, 0, 0, 1, -4, and 2, 0. Yes, here we can see we are certainly getting closer in comparison to our original graph. Let's see what it might look like if we have half our function f times half of f of half x, This time, because we have a fraction, we know we're going to horizontally stretch. So each x coordinate needs to be multiplied by 2. Multiplied by 2 because we need to stretch, we need to get bigger. So we're using that denominator to tell us how much bigger we need to get, in this case, by 2. This time we're going to multiply each one of our x values by 2. This will provide us with -10, 0, -4, 2, 0, 0 will remain the same, 4, -4, and 8, 0. Let's see what this might look like. -10, 0, -4, 2, 0, 0, 4, -4, and 8, 0. It certainly did. It got wider, just as we would have expected. Let's see what might happen if not only we take our function value and have f of half x, however, let's also put in a f of -half x. We've already determined that we're going to horizontally stretch by a factor of 2, but now we have this negative. And this negative also tells us that we're going to reflect across the y-axis. And this tells us that we're going to change not only the, reflect over across the y-axis. And if we reflect across the y-axis, that tells me that my x-coordinate is going to change from positive to negative. We have our original points. We're going to multiply by 2 and then change its sign because we're reflecting. So we're going to multiply by 2 and then change sign. -5 times 2 is -10. Change the sign, becomes +10. -2 times 2 is -4. Change the sign, +4. 0, 0 will remain the same. 2 times 2 is 4. Change the sign, provides us with -4. 4 times 2 is 8. Change the sign, we have -8. So we have 10, 0, 4, 2, 0, 0, -4, -4, and -8, 0. So we reflected across the y-axis. We're going to use the graph of f of x, our original graph that we've been working on, and build y is equal to -2, our function x minus 3 plus 1. So we have lots of things to happen here. There are a few things that are going to happen. This negative on the outside tells us that we need to reflect across the x-axis. This 2 on the outside of our function tells us that we're going to vertically stretch. The negative 3 on the inside tells us that we're going to shift right 3 units. And this positive 1 on the outside tells us that we're going to shift up 1 unit. So where do we start? Let's start on the inside of our function. This tells us that we're going to shift our graph 3 units to the right. So let's start by building the f of negative x minus 3 first and see what that will look like and kind of build from each piece to the next. So our original graph is negative 5, 0, negative 2, 2, 0, 0, 2, negative 4, and 4, 0. We know that we're going to shift our graph to the right. By shifting our graph to the right, that tells us that my x values will be added three coordinates to our x value. So I'm going to take my x value and add 3. Now we have negative 2, 0, 1, 2, 3, 0, 5, negative 4, and 7, 0. Let's see what this looks like. Negative 2, 0, 1, 2, 3, 0, 5, negative 4, and 7, which is off the charts. 7, 0. From here, let's look at the stretching, our vertical stretching. So let's move to the 2 of f of x minus 3. So we're going to use our points that we ended up with in our previous graph and now apply the vertical stretching by a factor of 2. If we're vertically stretching by a factor of 2, that tells me that my y values are going to stretch themselves by a factor of 2 since we're stretching and getting bigger. So we're going to take our y value and multiply by 2. We'll still stay the same with negative 2, 0, 3, 0, 7, 0. We'll now have 1, 4, and 5, negative 8. Let's see what this looks like. Great. Now what we need to do, we had a negative in front of the 2 times our function value of x minus 3. That tells us that we're going to have a reflection and we're going to flip across the x-axis. Our y values are going to change. Our y values are going to change from positives to negative or negative to positive. Let's put that part together now. All we need to do at this point, since our y values are different, or change their signs. So we're going to take the negative or opposite of y. All these zeros will remain the same. We'll now have negative 4, but now positive 8. Negative 2, 0, 3, 0, 7, 0, 1, negative 4. So now our point is down below, and then our curvy part is up above. The last thing we need to tackle is shifting up 1 unit. And then we've put it all together step by step. The positive 1 tells us that we're moving up 1 unit. If we're moving up 1 unit, that's affecting our y coordinate. So we need to take our y value and add 1 to it, giving us negative 2, 1, 1, negative 3, 3, 1, 5, 9, and 7, 1. And then we'll see what this will look like. Negative 2, 1, 1, negative 3, 3, 1, 5, 9, and 7, 1. So everything is shifted up 1 unit. So now we've put all the pieces together step by step, building from the very inside outward until we did the up and down piece very last. And this concludes our lesson on 2.5 regarding transformations of functions.